Hello, welcome back. Let us continue our discussion on the standard formulation and canonical formulations of a linear programming problem. To understand this, let us take a very small example over here. This example is an example of maximization problem with two variables and two constraints. And both the constraints are of less than equality type. And now to convert this into standard formulation, which should have these four conditions satisfied. The first one is the objective function should be either in maximization or minimization. We have that. This objective function is in the form of maximization. The constraints should be equality type. The constraints are yet to be in equality type. The right hand side values of the constraints should be all non-negative. That is okay. The distance variable involved should be all greater than or equal to 0 up to now is okay. So now let's first convert the inequality into equality. To convert the inequality of less than equal to type into equality, we need to add a slack variable on the left hand side of the constraint so that this inequality becomes equality. So let's do that. This is the one that I have. In this, what we've done is we have added S1 to the first constraint, S2 to the second constraint. This S1 and S2 represent its select variables, which convert the less than equality into equality, and both this S1 and S2 are also greater than or equal to 0. Now let's come back and check this condition again. The objective function should be either maximization or minimization. That is okay. The constraints should be all equality type. That also is okay. The right hand side should be non-negative. That is there. All the distance variable involved should be greater than or equal to 0. That also is there. So all the four conditions are satisfied by this problem, and hence this is a standard formulation of this linear programming problem. Hope you have understood this one. Now let's check whether this particular standard formulation that we have is also a canonical formulation or not. So to do this, let's go back to the canonical conditions and bring and see whether those conditions are satisfied by this. So what are the conditions that we had in the canonical formulations? So the canonical formulations should have one second. Yeah, let me do one thing. Let me take out this. See, the canonical formulation should have this four conditions. Along with this four conditions, you should also have this three additional conditions. 1, 2, 3 additional conditions. The objective function should be purely in terms of non-basic variable. The total number of basic variables should be equal to the total number of constraints. Its constraints should have exactly its constraints should have exactly one basic variable. So what we do now is we now partition the variables involved. We have four variables involved over here. Let us partition this variable into basic and non-basic. The selection of the basic variable should be such that this variable is involved only in that particular constraints, and it should not be present in the remaining constraints, and the variable should also have a coefficient 1 in that constraints. So when you look into these variables in both the constraints, we can say S1 is present only in this particular constraint with 1 as the coefficient. So this S1 is eligible to be selected as the basic variable. And you should have another basic variable from the second constraint that should also have the same condition. That variable should be present only in that particular constraint, not in the other constraints. And the variable should also have 1 as the coefficients. So S2 is the other variable that we can select because this variable is present only in the second constraint with coefficient 1 and is absent in the previous one. So we have partitioned the variable into basic and non-basic. So the basics, that variable that we selected are S1 and S2. Remember, the number of basic variables should be equals to the total number of constraints. The total number of basic variables should be equals to the total number of constraints. So the total number of constraints that we have over here are 2. So the number of basic variables should also be equal to 2. S1 and S2 are a basic variable then. So the moment you say this S1 and S2 are basic variable, the remaining variables of the problem, which are X1 and X2, should fall into non-basic variable. So the variable has been partitioned now into basic and non-basic. Now the objective function then should be purely in terms of the non-basic variable. Let us check that the objective function should be purely in terms of a non-basic variable. The non-basic variable are x1 and x2, so the objective functions are now purely in terms of a non-basic variable. So this condition is okay. Total number of basic variables should be equal to the total number of constant. That also is okay. The total number of constants is 2. The total number of basic variables also is 2. That also is okay. Is constant should have exactly one basic variable with coefficient 1. Is constant should have exactly one basic variable with coefficient 1. Is constant should have exactly one basic variable. Over here, this is the basic variable, and the coefficient of this basic variable should be equal to 1. That also is okay. And similarly, for this constant, s2 is the basic variable, and this also has a coefficient 1. So this particular formulation, which was the standard formulation, is also a canonical formulation if you select S1 and S2 as the basic variable. So a standard formulation sometimes can also represent a canonical formulation. Depends on the variable, the basic variable that you define over here. So this is a standard formulation as well as a canonical formulations as per definitions of the canonical and the standard formulation that we know. Now let's check whether every standard formulation is necessarily a canonical formulation also. To do this, let me consider another example. Let me say this is another example that we have. Okay, 1 second. Let me bring this one also. Yeah. This is another example of the linear programming problems where all the constraints are of equality type, and we have a maximization is as an objective functions, and there are 4 variables in the problem. Now these conditions of the standard formulations are satisfied by this condition of the standard formulation are satisfied by the given linear programming itself. The objective function is maximizations, all the constraints are of equality type, the right hand side values are non-negative, the variables are all greater than or equal to 0. So the given problem itself is a standard formulation of the linear programming problem. Now, whether this standard formulation also is a canonical formulation, we'll have to check. Now, so looking into this, the standard formulation demands the variable to be partitioned into a basic and non-basic variable. So we'll have to select the 2 basic variables from the 4 basic variables that from the 4 variables that we have over here in such a way that that basic variable is present in that constraint only with coefficient 1. And what we can do is we can say x1 as one of the basic variable because this is present only in this particular constraint and with coefficient 1. Okay, even if you don't have a coefficient 1, you can divide both sides by that particular coefficient to convert the coefficient into 1. Now what we do is we select x1 and x2, but the problem is x2 is present over here. Each particular constraint should have exactly one basic variable. The moment you say let's x1 and x2 be the basic variable, then you'll have to remove x2 from the first constraint using the second constraint, so that this particular first constraint is purely in terms of x1, the first basic variable. So what I do is I'll find out the value of x2 from here and replace it here so that this particular constraint becomes purely in terms of the first basic variable is x1. This is what I've done. See, x2, if I find out from here, is 26 minus 3x3 and 3x4. This is one. After solving, you find this particular equation. Now, this first constraint is now but converted into this one, which is purely in terms of x1, x3, and x4. x1, I'm going to take as a basic variable. x1, what I'm going to do is I'm going to take x1 as the basic variable and x2 is the second basic variable from the second constraint, and the remaining variable which are x3 and x4 will be taken as the non-basic. Okay, So the moment I say I take x1 and x2 as a basic variable, then the two constants should have the first constant. Suppose the first constant, if I want to put only in terms of x1, then the x2 should be taken out from here. So to take out x2 from here, I'll be using the second constant that I had done over here. Now this particular these two equations are now being converted into these two equations. Look into these two equations. The first equations, you have the first basic variable with coefficient 1. In the second equation, you have the second basic variable again with coefficient 1. On the right hand side are also positive, right? Now we still have a problem. If you look into the objective function, you have both the basic and non-basic variable. But the canonical formulation demand the objective function should be purely in terms of the non-basic variable. So you'll have to remove x1 and x2 from the objective function so that this particular formulation becomes a canonical formulation. So what I'll do is I'll find out the x1 value from these equations and x2 values from this equation, put it here, and write the equation of z purely in terms of x3 and x4. This is what I've done over here. One second. Yeah, this is what I've done over here. I have find out the value of x1 from these equations, put it here, x2 from this equation, put it here, and this is the new equation of z. And the new equation of z is now purely in terms of the non-basic variable. So now your canonical formulations to the linear programming problem can be written as z equals to 141 plus 3.5 x3 plus 0.5 x4. This is the objective function subject to the constants. Now the constants should be purely in terms of now this constant should have exactly one basic variable with coefficient 1, and the first constant basic variable is x1 and it has a coefficient of 1 equals to 34. The second constant basic variable is x2. It also has a coefficient 1 plus 3x4 equals to 26. Okay, and then you have x1, x2, x3 and x4 are all greater than or equal to 0. So if you look into this particular formulation that we have, this is a canonical formulations. This is a canonical formulation. This is a canonical formulation with basic variable x1 and x2 and non-basic variable x3 and x4. The objective function should be either maximization or minimization, that we have it here. All the constants should be equality type, that also we have it. The distance variables should all be greater than or equal to 0, that also we have it. The right hand side values of the constants should be positive, that also is okay. The objective functions should be purely in terms of a non-basic variable. These are a non-basic variable, so the objective functions are purely in terms of a non-basic variable. The total number of basic variables should be called the total number of constants. The total number of basic variables are 2 and the total number of constants is 2. So that also is okay. And its constants should have exactly one basic variable. Its constants should have exactly one basic variable with 1 as the coefficient. That also is there. So we have seen that the initial problem was in the form of standard formulations. Till the time we do some arithmetic like this standard formulation was not put in the form of canonical formulation. So a standard formulation is not always necessarily a canonical formulation, but if you look into the canonical formulations, a canonical formulations is also standard formulations. Okay, so this is how you convert a given linear programming problem into its canonical formulations.